take any of my equipment down there. He has a good camera, and so I was giving him some pointers. We ended up with a really great picture of the eclipse, and saw some little flares coming off the side and stuff. That was great. Prominences, they're called. Anyway, welcome to Science Sunday. It's been a good year. We've got one more month left, and for the past few third Sundays, which I guess in a way I'm responsible for, we started a series here, and we talked about water, and then my husband Dave talked about salt. And did you know, I want to give him a shout out, did you know the night before his talk, he's like, this is gonna be so bad, I just, people aren't gonna like it, I don't have enough information, I just don't feel great about this talk. And I've said, it's okay, you know more than anybody else in the audience about it, unless they're a chemist, and we'll tell them not to come. And so he did that. He did a good job, and he was the morning of nervous and everything. And so he arrives and he walks up to the microphone, and you know what he forgot? He forgot his notes. So he gave that whole talk on salt without even his notes, and he did a great job. So good job. Yeah, and then while we were at the eclipse, Scott gave us a talk about disaster and emergency preparedness, and that was well received and very timely. We're entering tornado season, so that was great. Thank you for pinch hitting for us, and welcome back at any time. And any of the rest of you, you know, Science Sunday isn't the Mike and Scott show. It's your show. It's to share information and knowledge you have about the wonders of the way the universe works. Everything from microchemistry to quasars and galaxy clusters. So if any of you have a topic that you're passionate about, have read up on, or are wanting to read up on, feel free to approach us, and you can give a little science talk. In fact, one of the things we're going to do this year that we haven't done for a few years is the final Science Sunday, the third Saturday in May. We want to do a Science Slam. Do you remember the Science Slam? If you've got, we've had Carl Nash talked about red-winged blackbirds, I think, and Bob, you talked about bicycle wheels, was it? Yeah, gyroscopes, and yeah, and so we've had a couple of talks, and typically, 10 or so minute talks, plus or minus. Let us know. Send us an email. Talk to us after today's Science Sunday. We'll probably send out, Mike, you'll send out a little note about it as well. And hopefully we can get 4 or 5 or 6 people together to give a little presentation about some interesting science topic. It could be social science, could be psychology, medical science, astrophysics, molecular chemistry, you name it, right? If it has to do with the way the universe works, we're interested in it. All right, so today, I told you about the first talk was about water, and then Dave gave a talk about salt. Today, we're going to have a science talk about another common material that still has some mystery and allure to it, and that's going to be soap. But you can't really talk about soap and the way these things react with other chemicals without talking about the star of the show of all interactions, and that's electrons. So we'll talk a little bit about electrons and their importance in chemistry as well. And this will be done by our dear friend and frequent contributor, Dr. Joanne Reed. So please welcome Joanne to the podium.
All science talks have to begin with a demonstration. This is the first and last chance to screw up the whole thing. One of the things I learned in sales years ago is that your last chance to lose the order is the demonstration. And so here's my chance to lose the order. I hold in my hand the It's Nemesis oil. This is Crisco pure vegetable oil. Microphone. I wonder. Let's see, what does it say here? It says that it's food. Okay, total fat 14 grams, saturated 2 grams, trans fat, monosodium 3 grams. In essence, it's a mixture of oils. So we've got some saturated oils, we've got some unsaturated oils, different chain lengths and that kind of thing. But as we all know in the kitchen, once the oil is on the counter, you can't get rid of it. It just is everywhere. And so what problems do we have with it? Well, oil, of course, is flammable. So the last thing you want to do is add water, because the flames just go along with the water, and pretty soon your house is afire. So you don't do that. Bicarbonate of soda, yeah. Put the lid back on the pot, yeah. The other thing is, it doesn't dissolve in water. They hate each other. And so we're going to see that. This is the demo. This is the part that has to work. Ready? This is a non-quantitative transfer. So now you can see we got 2 layers. We got water on the bottom. I'm back to the microphone now. We got water on the bottom. Water. You like that? Am I from Boston? It's water. And it's in a bottle. Okay? So we can see that there's water on the bottom and oil on the top. And if I try to mix them, the globs come back together, and pretty soon I have water on the bottom and oil on the top. It's a mess. It doesn't work. So, what do we do in a situation like this? We turn to our handy-dandy detergent. I have enough here, barely enough. Once again, a non-quantitative transfer. Okay, so I'm just going to let that sit there, and we'll go on with and it'll sit there, and we'll see what happens. All righty, where's my clicker? Did I lose my clicker? Yeah. The importance of being organized. All right, so we're going to talk about electrons, we're going to talk about chemistry, we're going to talk about surfactants. Hey, this is a soap story, sort of like a soap opera, but totally different. Wrong what? Chemistry at work. We got electrons. Now, in the past, we talked about all sorts of gravity things. We talked about neutrons, we talked about protons, we talked about galaxies, we talked about stars. And as though those were important, they're not. The only important thing in this universe is the electron. Everything else is garbage. Why? Electrons are the workhorses of the universe. Electrons are electricity. Electrons are magnetism. Electrons create light. Let there be light only after you have an atom. Let's take a look. Where is our good friend here? Here is an electron right here with leptons and everything else. It's a really small, we've got quarks up here and bosons over there. Bosons, you like that word? It's a boson. And if you called a kid that in school, you'd have got punched, right? And then the leptons with the electrons and all that kind of stuff. So this is an elementary particle. It's one of the most, it's in the beginning kind of stuff. And then we talk about hydrogen, the very first atom. And it's the only atom that we can fully compute. Niels Bohr did this many years ago, Niels Bohr, and he just figured out what the atom was. And essentially what we have here is a nucleus. Whoops, we'll go back. We have a nucleus, and swirling around the outside is an electron. Now you say to yourself, now wait a minute. The nucleus is a proton and it's got a positive charge. And the electron's out here and it's got a negative charge. Why don't they just sort of bump into one another and go away? Great question. A poor answer is, if we did that, we'd come up with a neutron. And the neutron would fall apart in 18 minutes, becoming a proton and electron. It's not satisfying, is it? So the answer we scientists have to this is, because that's the way it is. Science is terrible at why. We don't do why very well. We do what, and we do how, and we do when. Why? It's an atom. And if it weren't for atoms, we wouldn't exist, so we say, yay, atoms. Now, sizes. This is the size. This is at 1 angstrom. Now, this is an impossible number for us to think about. 10 to the minus 10 meters. This is a silly number. So how big is this really? Let's picture this building. And let's go to the biggest wall. And we'll take a common pin and we're going to go right to the geometric center and we're going to stick a pin in the wall. And then we're going to put a string and we're going to make the biggest circle we could possibly make. And then we're going to cut off the pin right at the wall. You've got a nucleus. It's really small. You've got an electron. Oh, so what's an atom? It's space. There's nothing there. And then there's this little bitty dot called the nucleus. And somewhere out there is this thing that's wandering around creating almost a sphere of electricity. These things are really weird. Let's talk about sizes for a minute. The proton is 10 to the minus 15 meters. That's a femtometer. The electron is 500 times 10 to the 21st, which is a zeptometer. Now, that's a grouchometer and a zeptometer and a harpometer, right? Yeah, these things are really, really, really small. And the question, of course, is why don't they fall apart? And it's a good thing is they don't. Yay! Again, sizes. When we begin talking about these things, we talk about protons and neutrons, and we give them a value of 1. The big difference is that the proton has a positive charge, the neutron has none. And then there's an itty-bitty little electron down here. Itty-bitty little thing. 1/1800th of the size of the ether. An interesting fact I picked up just the other day. How long will an electron live? This is a minimum. An electron will live at least 6.6 times 10 to the 28th years. Again, a stupid number, huh? Our universe is 14 billion years old, thousands, millions, billions. So 2 times 10 to 1 times 10 to the 10th. So this is going to live about 3 universes long, at least. So we don't have to worry about them going away anytime soon. Now, when we talk about light, we talk about, again, our nucleus and our electrons zipping around the outside. It's at a specific distance, a specific radius, a specific energy. And what happens when we heat hydrogen? We get hydrogen going, and it gets all excited. And it spins, and it vibrates, and it goes back and forth all over the place? Energy. Some of that energy is at exactly the right wavelength to excite our little electron right here. Our little electron going around here, and it bounces from here to there. Again, a specific energy state. It can't exist in between. Again, we ask why, and the answer is yes. But it does. Now, what happens when it begins to cool off a little bit? When it cools off a little bit, the electron drops back down to where it was. And in the process gives up energy. And the energy it gives up is a photon. It's light. Oh, let there be light? First off, you have to have an atom. Then you have to have an electron. And then you have to excite it. And then it has to calm down. And then you get a photon. Now, what I'm looking at here is the emission lines. This is essentially the sun, a continuous emission. This is what, if you heat up hydrogen, this is what you get when it emits light. It's very, very specific points. Nothing in between, just these particular energies. Now, the other half of it is, if you shoot a photon of exactly the right energy at the hydrogen, it'll soak it up. It'll suck it up like a sponge. And so we see that the spectrum of emission output is exactly the same as the absorption input. Now, we talked earlier about the early universe and said it was dark. We couldn't see anything. What was happening? Well, the hydrogens were all emitting lots and lots and lots of photons, but the other hydrogens were absorbing them. And nothing happened until, finally, there was a breakthrough. There was enough energy that we separated the nucleus and the electron. And suddenly, all you had was bare protons. Well, protons don't do light. They don't know anything about light. And so, once that occurred, the light could go a little further and a little further. And so it took millions and millions of years for us to ionize enough of the hydrogen that the light could finally escape. And that's the edge of the visible universe and why we have a dark period in the universe. And so, again, hydrogen and light. Also, electricity. Well, electricity, yeah, okay, I'm getting that. Magnetism. What's magnetism? Well, if we took molten iron and put it in an electric field, so there's a positive and a negative, and let the iron cool down. All of the electrons are aligned. And so there's a positive and a negative to that piece of iron. Magnetism. Photons, electricity, light. All because we have electrons. And chemistry. Yay! Chemistry. That's why we're here. Table of the elements. A bit confusing at first because there's a lot of them. And we're going to look at all of these things. I'm going to concentrate first off on hydrogen and helium. And we're going to look at it. And these are symbols. These are important symbols for us to recognize. These symbols are developed and named and done by the International Union of Pure and Applied Chemists. We're the ones that do all the work. We specify the names, we specify the weights, we specify everything about them. So it's the International Union of Pure and Applied Chemists that are responsible for the names, also responsible for getting the data so that we can put it in this particular form. There's the symbol, the name, the atomic number, the atomic group, and the class. Here's the number of protons, not the number of neutrons, just the number of protons. So this is the fifth element in the series. Here's the actual weight of the whole of a mole, if you will, what we call a mole of boron. It weighs 10.811 grams. So if I look at hydrogen and I say, what is hydrogen? Well, over here we have a nucleus and a shell. The shell contains the electrons. This is the energy band. The particular energy band is the s electrons. Each shell is divided up into orbitals. Ready? Orbitals. So we got a K, an L, an M, and an N shell. And each one of these has electrons in it that are in orbitals. The K shell only has one orbital. The poor little K shell. Oh, we weep for it. But then there's a more robust L and M. And now we get out to N and O, and they get lots of them. Because they're big and strong, and they ate their Wheaties. Now, what happens next? Here's helium. And notice that helium has 2 electrons. Well, this is the coolest thing in the whole world. What has happened? Electrons have a spin. They want to match up. As long as there's a spin sitting out there in that atom, it really, really wants to do something with it. What it's looking for is a complementary pair, so that they neutralize the spins. And in this case, helium has the 2 electrons, and they have neutralized the spin. So hydrogen has a positive, as a half spin. Helium doesn't. Helium is spin neutral, if you will. And therefore, helium doesn't do anything. Helium hangs around and looks at the universe, and, it's a nice place. Whereas hydrogen, with that one lone electron, is going, help! Somebody, somewhere, help! So I look back here now, and we see hydrogen and helium. And now let's look at the next row. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and now, this is interesting. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. What are these? 10. This is the key. 2, 8, 8, 18, 18, 32, 32. That's the order of the electron fill in all atoms. So these 2 rows, this row here and this row here, will have an additional 8. Okay, let's look at that. There they are: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So let's start with our friend helium, and we're going to add 1 proton and 1 electron. Notice that when we do that, the atomic weight is not 3, but is now 7. We have 3 protons and 4 neutrons. What are the neutrons doing? The neutrons provide the energy to keep the protons together. 3 positive charges are not going to live by themselves, not glammed up together. They need some glue to hold them together. And that's what neutrons really do inside of a nucleus. They provide the glue that holds it together. It's called a strong force. The neutrons actually give up some mass to create the force that holds this together. And so it's a combination of protons giving off that good positive charge and the neutrons holding them together that keeps the electrons in orbit. And in this case, once again, we have the L shell with an S orbital. It has 1 lone electron sitting out there going, "Can I hitch a ride with somebody, please?" Yeah, lithium is active. It likes to do something. It doesn't sit around well all by itself. It does not, but it does work and play well with others. We go on to beryllium, and now beryllium has filled up the S shell. Beryllium doesn't do much. So again, if you have a bare electron, it's looking for somebody. The moment you pair it up, it goes to sleep. Okay. Now, you don't want to mess with beryllium. That's been tried. Don't leave it alone. It was used a lot in the atomic programs in the early age. They tried to machine this stuff, and everyone who did died quickly. Yeah, we make believe that beryllium doesn't exist. Boron. Oh, here we are. This is the next transition. We filled up the S orbital, and now we're working on the P orbital. That's where those extra 6 come in, the P orbital. Now this has one lone, it's sitting out there all by itself. Boron is quite active, boron oxides, boric acid, gypsum. Yeah, we use a lot of that stuff, and it also, of course, is a wonderful neutron absorber, which we use in nuclear reactors. Carbon. Oh, praise be carbon. All praise to carbon. If it weren't for carbon, none of us would be here. So we will discuss carbon in a lot greater detail. Notice that we have 2 p electrons, and they're sitting there all by themselves. They're not paired up. And you say, why? Oh, no, remember, we don't do why. No. This is how it is, and this is how it works. So, nitrogen. Nitrogen has 3 unpaired electrons. So what is this saying? Well, the boron can react with 1, and carbon can react with 2, and nitrogen reacts with 3? Is that what we're saying? Yes! That's exactly what we're saying. The number of unpaired electrons is a measure of how reactive it's going to be. Oxygen. We've paired up. Here's the first pair of P's. Notice now we only have 2 available electrons. Fluorine. Now it's only got 1. And neon. They're all paired up. Neon is inert. You can't do anything to it. It glows in the dark, add a little electricity and it glows. But it doesn't react with things. Actually, you can, but it's brutal. You got to really force it. And so we talk about electron bonds. An electron bond is a pair of electrons, one coming from one atom and one coming from the other atom, and pairing up. And this is the secret, if you will, of chemistry. So, lithium fluoride. Lithium has 1 lone p level electron. If I look over here at fluorine, those 2 are paired up, those 2 are paired up, but there was a lone one here. And so they match up. Now, both of these atoms have 8 p electrons because they shared 1. And that's the basic of all chemical reactions. They share the electron. Now, what's the nearest available? Now, hydrogen. When the universe started, it was 3/4 hydrogen and 1/4 helium. Right now, 14 billion years later, it's 3/4 hydrogen and 1/4 helium. Oh, and something else messing it up, but that's how it. So, what's hydrogen going to do with that lone electron? It's going to work with the next electron, the next hydrogen, to pair up the electrons. H2. Hydrogen doesn't exist as H, it exists as H2. The same thing is true with nitrogen. The same thing is true with oxygen. The same thing is true with fluorine and chlorine and bromine and acetylene and all of those others. They're going to hitch up with themselves first if they can. We write a shorthand. This is just a shorthand way of, I'm going to react lithium with fluorine to make lithium fluoride in the same way that I can take carbon and oxygen and create carbon monoxide. Carbon monoxide. 2 bonds. The 2 p electrons of the carbon and the p electron available in the oxygen creates the double bond. This is carbon monoxide. Colorless, odorless, tasteless, deadly. It gets into your blood and takes over from the oxygen and displaces it completely, and you die. So, not a friend. Now, at the same time, there are 2 other electrons, the 2 s electrons that are available. And typically we say, at the s level, are they really available if you got p level? And the answer is no, in most cases. Carbon is unique. The energy level difference between the 2 s electrons and the 2 p electrons is very, very small. In others, it's quite large, and you need an energy gap to jump over them. But in carbon, they're really, really close. So if you have enough energy to react with those two P's, it's probably enough energy to activate the two S electrons. And when that happens, you hit the wrong button. Carbon plus hydrogen. Carbon plus hydrogen creates methane. One carbon, 4 bonds. Now at this point, there's no difference between the S and the P electrons. They're all the same. They're all the same level, they're all the same energy. The single hydrogen is paired up with the carbon. The carbon has all of these extras. It was looking for 4 electrons. 1, 2, 3, 4. Everybody's happy. This is a wonderful little molecule and is the basis of practically everything in organic chemistry. For all the chemists out there, no, this is not a balanced equation. So carbon plus hydrogen is methane. Now, can we have 2 carbons? Sure, carbon can attach to carbon. Why? Sure, absolutely. And this is the secret of all of life and all of the things that we know. Carbon attaches to carbon in chains that can be as long as you want, in chains that can be as complicated as you want. Carbon to carbon. Now, as people say, well, carbon and silicon are sort of similar, aren't they? Yeah. But what happens when you add oxygen to silicon? You get silicon dioxide, which is glass. What happens when you add oxygen to carbon? You get carbon dioxide, which is a gas. It goes off, no problem, the reaction continues. If the reaction turns to rock, it isn't going anywhere. And so this is one of the huge differences between silicon and carbon. I can just do almost anything I want to build a carbon chain, and I cannot do the same thing with silicon chains. Oh, darn it. Basic properties. If we think about the carbon length, carbon 1 through 4, methane, ethane, propane, butane, words that you all know. Methane is 1, ethane is 2, that's stove gas. Propane, right, you go out to the bar and you get your canister, and now you're cooking on your grill. Butane, your cigarette lighter. These are all gases at room temperature. As we go up about C5 to 10, something in there, it's a oil. Pentane, decane, heptane, octane. Octane, gasoline, yes. We all know the smell of gasoline. It's wonderful for cleaning. I know my dad was an automobile mechanic, and his hands would just be greasy, all gooky. And so he'd wash his hands in gasoline to get the oil off, and then wash his hands in soap to get the gasoline off. Yeah, so that was a common trick. You keep on going. You get up into the C10, 13, 15, 20. They're all greasy. Yeah, they're liquidish, sort of like butter, if you will. So, and then you get beyond that, and they become waxy, like a candle wax. It's sort of solid, but it can melt easily. And as you keep going, it gets more and more and more solid. What's the top limit? There is no real top limit. Super high density polypropylene can have 100,000 chain length really easily. So these things become just enormous numbers. Yeah. Polyethylene, polypropylene. By the time we're talking about the plastic stages, we're in the 100 to 200 to 300. The most common reaction that we have is, of course, we get this stuff and there's air all around. And so we talk about the oxidation of carbon compounds. Here's our oxygen again. And remember that our oxygen has these 2 available p electrons. They want to do something. They're really eager to do something. And of course, our carbon has, as we now know, has actually 4 available electrons, the 2 p's, and enough energy to pick up those 2 s's if we can. And so we have a whole family of things that can happen. We start out with methane. If we oxidize methane, essentially what we're going to do is we're going to stick an oxygen in between the carbon and the hydrogen. And it's going to look like that. This is an alcohol. Methane, methanol. OL is for, so if you hear the OL, you know it's an alcohol. I can go one step further in my oxidation process. I can get rid of another hydrogen. Ooh, what's this? This is an analog to the carbon dioxide, we talked about. But the oxygen is double bonded. This is a carbonyl. This is an extremely stable component. Once you have a double bonded oxygen to your carbon, it's going to stick around. You're not going to get rid of it easily. This is an aldehyde, methanal. So we've gone from methane to methanol to methanal. And can we oxidize it one step further? Sure. One step further. This is the acid. This is an organic acid. In this particular case, we would call it methanoic acid. Now, these are not words that you use every day. Let's use the words that you use every day. Methane, wood alcohol, formaldehyde. Remember the stinky stuff when you were in your biology labs, you open up and you're going to get and you went, oh God, what is that? It's formaldehyde. And this is formic acid. Why formic acid? Ants. Grind up ants, extract with water, and you will get formaldehyde. Formicidae. Formic acid, formaldehyde. These are the common words we use. When we go over into the ethane group, we see cooking gas. This is the gas that you have in your stove. Drinking alcohol, yay booze. Acetaldehyde, and acetic acid, which we also know as vinegar. Oh yeah, so these are common things that we have all over the place. These are just not the standard chemical names that we would use. What happens when we begin to add more carbon lengths? 2, 3, 4, 5, 10. Things get really complicated really fast. Because now, where's the carbons? Where are they going to hitch to? Oops, I've got to go back one. Here is propane, propyl alcohol, and you can put the alcohol in the middle. This is isopropyl alcohol. You go to the store and you buy isopropyl alcohol. It's in the bottle. You buy it and there you got it. Propyl aldehyde. Oh, what's this? This is new. It's still an aldehyde type thing, but it's even. This is acetone. Again, go to the store, buy acetone. What does it do? Nail polish remover. Marvelous. And you know the smell of acetone. That's typical of all ketones. And propionic acid down here at the bottom. What happens when we go to butane? Oh, now we've got all sorts of messes. Not only can you have the straight line, but you can have the methyl group sticking out of the middle. Oh boy. And so, what happens when we start to oxidize this? We can have the straight chain, but we can have the alcohol here, or the alcohol here, or the alcohol here, or it gets to be a mess. Very, very, very quickly. So we're going to stop at 4. We're not going to go to 5. No. So here's butylaldehyde. If I put it in the middle, this is methyl ethyl ketone, MEK, the chemist's delight. This will dissolve plastics. Oh, it's marvelous. And it's got a low enough vapor pressure that it will evaporate. Oh, MEK. We live with MEK. It's fun. And butyric acid. Butyric acid is beginning to get smelly. By the time we get to caproic acid, which is goat odor, yeah. We had an experiment in college where we were using caproic acid and we were making esters of caproic acid, and we messed up, and it went all the way down from the 4th floor to the 3rd floor to the 2nd floor to the 1st floor, and right at the bottom there was the president's office. That experiment was never run ever again in the school, ever. Esters. Oh, now we've come to the great smells that there are in the world. An ester is the combination. Now, we've talked about the ability of an acid to react with something like sodium, and we get a sodium acetate. Well, we can also react the acid with an alcohol. And so this is ethyl acetate, acetic acid and ethanol. These are the great smells of this world. Oh, you talk about perfumes, you talk about fruits, you talk about veggies. This is where the smell comes from. Apple, banana, orange, nail polish, yeah, nail polish, wintergreen, rum. All the smells, all of them that you're going to have, are going to come from an ester. And when you get to perfumes, it's going to be a combination of esters and long-chain alcohols that make up those smells. Now, we don't have to have just a single alcohol. We can have multiple alcohols. We can have things like glycerin and ethylene glycol. And, of course, we get the same kind of reactions here. There's acetic acid with glycerin, and we're going to have acetyl diglyceride, acetic acid with ethylene glycol, and this is acetyl triglyceride. Big difference is, in general, huge generalization. This is vegetable, this is animal. Okay. Animal fats have very commonly triglycerides, and more commonly in vegetables we get the diglycerides. Now, these can be saponified. That is, we can undo the ester. And so in World War II especially, when we were told to save our bacon grease and turn it into the government, what were they doing? They were not as interested in the acids, but in the glycerin. Glyceryl trinitrate, nitroglycerin. That's what they were looking for. So they were just relying on every housemaker in the world to make a bang. Now, we talk about the reactions that can go on. We talk about the ability of long chains to fit in long chains. Oils are not soluble in water, but oils are soluble in oils. Salts, the kinds of things that Dave Clark talked about just 2 weeks ago, when we had an ionized thing called sodium chloride, and we could create ions that went right into water just perfectly. The problem, of course, with grease is, how do you get grease into water? Well, what would happen if we had a compound that was oil on one side and salt on the other side? Ooh, the oil part would grab the oil, and the salt part would grab the water, and it would dissolve. Cool. And so, we can create this kind of an object. So, we take the acid and we react it with sodium, for instance. As a for instance, we don't do that much anymore. And we can create what's called an emulsion. So the emulsion, the long chain fatty acid type things, combine with the long chain of the soap. The other half of it is dissolved in water, and so we have this single compound dragging the oil into the water. Well, not quite. We're going to create emulsions. And there are basically 3 kinds of emulsions. The first kind is the oil in water. That is, the long chain is sitting there. We take the long chains, big long chain, and we grab oil. And on the outside is the salt that grabs the water. And so there's a globule of oil inside a droplet of water. It's equally possible to do it the other way. That way we have an oil in water emulsion. So you've got a drop of water, and inside of that is the salt, the sodium chloride type salt, and on the outside is the long chains, and that's holding onto the oil. And the third one is equally possible, and that's the bubbles. We all know if soap, you have to have bubbles in order for soap to work, right? And that's where there's the bubbles. So here's our bubbles, air, oil, and water. So we're making a nice foamy bubble. Now, what we're going to have here is we have all three. Down the bottom, in the blue layer, we have the oil inside of water. You see how cloudy it is? It's got little bitty globules. In between is a white layer. That's the water in oil. And up top, we got foam. It's actually working. We've got soap. It works. It will break down the soap, it'll break down the gook and yolk and everything else that's on your kitchen counter, that's sitting on your dishes. You can wash your hands. You can actually get things clean. And this is what we do. It's an emulsion. Emulsion's a break. Yeah. Think milk. Milk is an emulsion. How can you break that emulsion? You heat it. It falls apart. Add salt. It falls apart into your curds and whey. Without our curds and whey, we wouldn't have Little Miss Muffin. But there's your basic chemistry. How to do things in one. Chemistry in action. So this has been Electrons, Chemistry and Surfactants, a soap story. Ta-da! Now that you're all chemists, and you can all go out now and get your Nobel Prize.
So how do you get rid of it? Once you get the mixed, how do you get rid of it?
Oh, add water.
With more water?
Yep, just at that point, you can just take the water now, all of these are nice emulsions, and you can flush them out with the water, and they'll right down the drain, no problem at all.
And they'll separate again, or what?
Oh, it doesn't matter once they're down the drain. Yeah, they'll separate sooner or later.
They may go into the streams or whatever.
Pardon me?
They may end up in the streams, the lakes, or whatever. Right?
Your clothes are clean, but you pass this oil into.
Yeah, the oil goes down the drain.
Right, but it goes, what happens after the drain? Where does it go?
Oh, to your local area which cleans up water.
Do they separate it back out, or does it end up in the lakes
Ooh.
or the streams, or what?
Ooh, you have to ask those guys how they do things like that.
Okay.
Because it's a fairly complicated process. I know that in the water treatment plants. I'm not as familiar with it as I'd like. Again, the emulsion itself will break once you begin to add stuff to it. And so now you've got how they separate things in the water treatment plants. I don't know, but they do, and it's good that they do. Yay! Or it'd be a really smelly planet.
Earlier, you said something about without like foam or suds, soaps don't work.
Oh, when we were kids, and you were washing the dishes because there's no such. The children were the dishwashers, right? Okay,
Right.
And so the whole question of washing dishes was, is it nice and soapy water? And the way you told it was good and soapy water was because it created that foam. And the moment it said the soap was all used up, and Mom would say, "Well, add more," and So, yeah, it's an old wives' tale, but it works. There's an element of truth to it, that the air emulsion is really nice. It does work. It's just not necessary. In fact, if we go to non-ionic detergents, you won't have any foam. Also, on the other hand, we could add compounds to it, like for beer, to stabilize the foam. So depending on what you want to do, you add a little bit of this and a little bit of that just to stabilize it. Because again, the old wives' tale is, if it's soap, you got to have foam. You got to have bubbles. So it's a bubble bath for your dishes. Mhm.
I was just wondering because, there are some things that I think are non-foaming, like
Yes.
Cascade detergent and trisodium
Yeah, absolutely.
phosphate. And is that work like the similar principle?
Yeah, the non-ionic detergents work similarly, except they're non-ionic. But they use a slightly different mechanism. And this is an easier mechanism to explain.
Okay, thanks.
Because Dave just did salts 2 weeks ago, so I can piggyback on him. And he piggybacked on Scott, who did water. So, I mean, oh, God, we're good.
But this foaming that you're talking, that's ecologically unsatisfactory now, or not so good for the planet, right? They're trying to provide some of these detergents that don't foam because they are bad for the environment or
Yeah.
unsightly or...
Yeah, and if it weren't for our human perception that you need to have soap bubbles, we might. But again, it's like having beer without suds. There's something wrong with the beer. It's flat, whether it is or it isn't.
Would you call beer an emulsion like this, or is it...
We actually try to emulsify a certain amount of air in it, and that's where the foam comes from. But of course, again, that does fall apart. The best example of an emulsion is milk. Okay.
And
And-
milk will, if you shake it, you'll get a little bit of bubbles and so on.
Yeah, well, as you know, if you shake up milk, it'll bubble.
Yeah. So what defines it as an emulsion then?
Oh, the fact that it is not a solution and it's not a colloid, and that it does sooner or later break down. A colloid won't break down. A solution won't break down.
What was the second?
Colloid. A colloid is particles which are about the same size as the frequency of light, of visible light, and so they're small enough that the Brownian motion of the water itself is sufficient to keep them active and keep them moving around. You can break a colloid by heating it, boiling it, and then that'll kill it, or by adding something which destroys the material itself. I had 2 different gold colloids. I had a blue one and a red one, and there was a colloidal gold in what was it? Tannic acids. It's really cool.
More questions?
In my distant memory, I remember in high school them talking about a difference between soap and detergent. Am I remembering that there's a difference with ionic bonds being somewhat involved with that? Is soap different historically, especially ivory soap, for instance?
Yes, there are all sorts of different soaps. The particular one we're using here is sodium lauryl sulfate. So it's not just sodium laurate. Sodium laurate itself are harsh soaps. They're really tough on skin. So we use a sodium lauryl sulfate. We take the lauryl alcohol, react it with sulfuric acid partially, and then react that sulfuric acid with sodium. So you have a double salt, same way you have with bicarbonates and that kind of thing. And this is a softer, gentler soap on the skin and won't take the skin right off their bones. And it still works, but it still is a salt. But it's a sulfate salt rather than the direct salt. Can you use other things? We had phosphates, as you know, for many, many years, and these were just wonderful for cleaning and that kind of stuff. But then again, the bugs loved it. Oh, the blooms that we had, the algae blooms and everything else, and the Gulf of Mexico turned green, and it was really oaky. And so we had to stop using that. But yeah, there's an awful lot of ways of doing this. You can also use long chain alcohols. They're also very effective, so we can have some of those things which are non-ionic detergents. And there's a whole group called the betanes, which are really used in hair products. Again, because they're mild, but they do the job and they won't destroy the hair. And so that's a third category. Yeah, there's all sorts of surfactants. This is the easiest one to talk about. But yeah, you get into the world of surfactants and beauty products and that kind of thing. Oh, it gets exciting.
I was wondering about, Pioneers made soap
Yeah.
from animal fat, right? From
Oh, yeah.
lion animal fat. I don't understand the process. It seems like,
Well, again, the other half of the animal fat, let's go back here, if I can go backwards. Okay, there's your animal fat. So the other half of it is you can get, when you saponify, you break it apart, and so you end up with acids and the glycerin. So you take the acids and you react them, and again, you use things like calcium oxides, which you get from cooking limestone. So you can get the calcium salts and the sodium salts of the acid itself. The problem is there's a lot of lye in there. And boy, oh boy, they just take the skin right off you. And so soaps were available, but people liked to have the skin. They thought that was a helpful thing to have around.
useful.
Yeah, it was useful. And so it became a time when you had to wash it. And we began to figure out if you wash this soap several times in water, you get rid of the hydroxyls. You get rid of all of that kind of stuff. Can you neutralize it a little bit with an acid, for instance, some acetic acid, to help get rid of that? And yeah, again, and that helps you to dissolve it in water. And the soap itself is long enough that when the water goes away, you're left with this ooky mess. It's sort of waxy, oily stuff, and that you can pick up and use. So 99 and 44, 100% pure, it floats. Yeah, that's again, it's a different kind of, and the pumice that's in it is helpful to keep it going, and it aerated so that it floats and all that kind of stuff. And again, it's a good gimmick, but yeah, there's all sorts of different ways of attacking the long chain acids, long chain alcohols, long chain carbons, and just to get them out with the water. They don't have to be permanent. It doesn't even have to be really, really, really good. It has to only be sufficient that we can get rid of it. Because water we got tons of water.
Other thoughts or questions? John?
Ta-da!
Can you address how we get rid of germs like off our skin?
Couple of things. First off, let's remember that skin is really good at getting rid of all sorts of things. If you took a virus and put it in the palm of your hand, 10 minutes later that virus is dead. This stuff out here, this is really, really good. The problem is if it breaks. If there's a break in the skin, that's horrendous. There, of course, there's groups of bacteria and that kind of thing that can physically attack the skin and cause all sorts of problems. And those are a separate class. But in general, our skin is really, really good at. So what we're trying to do is wipe away the protective oil layer. So they're living underneath that. They're safe from the oxygen, underneath that oil layer, right up next to the skin. And now they've got the time to do anaerobic attacks. So we're good at taking care of things that air, oxygen. An anaerobic attack, that'll get you. And so we're concerned about that, and we wash that off, and that's good. Now, can a soap have antibacterial stuff in it, like Irish Spring or Dial or one of them? Yeah, sure. And for instance, if you're going in for surgery, they will tell you, here's the antiseptic soap, Dial or whatever. Go buy that, bathe using that, and so that when you get into surgery, your skin is relatively clear. And we're not going to run into all sorts of problems with, ookies.
So do the germs get emulsified
No, not generally. It's a not friendly environment. It's like if you put bugs, ants, into sugar, they'll die because there's no water. And so we're dealing with that kind of an equation. If you don't give it the right foods, you're going to kill them.
So basically, you're killing the germs by removing the oil?
Yeah.
Okay.
Yeah. And water, since we're water, we're good at water. We like water. We are.
What is high efficiency detergents which are used in modern washing machines?
Essentially, it's hyper concentrated. They are using a few additional things. This is high efficiency. Now, I look at it and I don't know if it has anything on here that's of importance to me. No, it doesn't have any good chemistry here. Okay.
They're usually bacteria munching globules like Pac-Man, right?
Basically, it's just hyper concentrated. They are using slightly more aggressive detergents as well. So they're using longer chains. They're using, again, sulfates and that kind of thing to really push it. The whole idea is to reduce foam. And that's the big thing. So they really take out all the foaming agents. So that when you look in your clothes washer, it used to be you had lots of bubbles on the top and everything else, and you knew it was working. And now you look at it and it's just water. And you go, what's going on here? Yeah, we're taking out all of the enhancers. So it's really getting back to basics. And how do we do that? We call it high efficiency. And I can charge you more for that.
Dave, I know you're city manager or working in engineering for Lyle, and is there a lot of things with detergents and
Oh, yeah.
so on with your
Oh, yes.
with your business, with your work?
Yeah, I'm assistant public works director for Lombard, and we co-own a wastewater plant. So they're amazing, mostly biological facilities, and we just give it time for the bugs to eat any nutrient. And there's also grit chambers and settlements, and they're amazing processes.
Yeah.
But yeah, it's largely biological. That's the
Okay.
least expensive way to process waste. And quite often around here, the water coming out of the plant is cleaner than the water in the river.
Are there things that concern you about detergents or getting rid of detergents or?
I haven't heard any problems with
No.
detergents. You know, phosphates you mentioned,
Oh,
and,
yeah.
yeah, and the blooms. That was a problem with too much nutrient coming through the plant to be able to process. But now that detergents don't have phosphates, it's a lot easier not to overwhelm the plant and have overflows that cause problems.
Yeah, they're primarily sulfates and long-chain fatty acids. And the bugs are going to just eat the fatty acids. That's called food.
All right. Well, thank you so much. It was a wonderful talk. We appreciate it very much. Nice job.
Thank you.